All right, so do we have sound? Yeah, I'm not sure. All right, so hello everybody. My name is Kevin. I'm a software engineer at Datadog, and I'm here with you today to talk about debugging, and more specifically, debugging one layer deeper. So yeah, we have the cats, that's perfect. So what do I mean by one layer deeper? Well, in the past, I've already talked about how to debug programs in your .NET application. But this time, I would like to focus on a more insidious kind of problem where the issue comes from the interaction with native code. And I think most of developers won't have to face this kind of problem during their job, or at least I'm hoping so. But by showing you how to tackle this kind of issue that looks overwhelmingly complex at first, and how to break it down into simple problems and solve them individually, I'm hoping that you will learn a few tricks that you can use for your own investigations. I will start with a few words of warning. First, I'm going to focus on the process rather than the tooling. So I will be showing some WinDBG command, and I will give only the minimal amount of explanation about them. If you are interested in knowing more, Tess Fernandez has a talk later today about advanced debugging, and I'm sure that she will cover this kind of stuff into more details. Also, there will be some assembly code, so don't worry, I will explain it, but if you have a phobia, that's a good moment to leave the room. And that's a detail, but the description of the talk mentioned LLDB. That's because it's the description for an older version of the talk, and I forgot to update it. So if you are here specifically for LLDB, which I don't think, sorry, there will be none. And so I mentioned methodically dividing the problem. And to do that, I use a simple process, which is 3 steps. And the first step is identify. You can't do anything without data. And so the first step is to get data about your problem. So at the beginning, it will be what are the symptoms, when did the problem start, what have you tried, and so on. And it's very important to make sure that this is verified data. You have no idea how much hours I've lost in the past starting an investigation based on the false description of the symptoms. So don't trust anybody, and don't hesitate to double check everything. When you have the data, you still need to do something with it. So you need to put it into context and make a theory about what is happening in your application. To me, this is the hardest step because this is a creative step. You won't find any step-by-step description about how to come up with a theory about a difficult problem. That's something you have to figure out on your own. And experience is going to help you a lot. And also, it's nice to have a few coworkers around to bounce ideas back and forth. And last but not least, when you have your theory, you still need to verify it. And more often than not, you will find that your theory is incorrect. And this is fine. This is part of the process because by discovering that this is incorrect and by understanding why, you will uncover more data that allows you to repeat the process. And every time you will be able to make a more refined theory until you finally manage to crack the case. So to illustrate this, I will tell you about a bug I investigated as part of my job. So first, I'm going to give a bit of context. I'm working at Datadog on the .NET Tracer. What is it? It's a component that you install on your server, and then without any modification of the source code, we're going to instrument your application. And we're going to detect whenever you have an incoming or outgoing operation, such as an HTTP request or a SQL query. And we will send that information to our backend, and then you can have a nice UI where you see a summary of everything that happened in your application. And the way we do that is by rewriting IL at runtime. So whenever you load a supported third-party library, we detect that, and we rewrite it to inject our instrumentation code. To do so, we use a .NET Profiling API. And it turns out that today you can't use managed code for the profiling API. You absolutely have to use native code, usually C++. And that's why lately I've been dealing with this kind of bug that comes from the interaction between managed and native code. So for the program itself, what were the symptoms? So we have a special test environment where we have 2 servers running the open source CMS Orchard, and they are receiving automated traffic. And the idea is that one is a baseline server, so it's running the application as is. And on the other one, we run with the Datadog instrumentation, and then we monitor both servers to find any difference in behavior that could be caused by our instrumentation. And at some point, we noticed that the instrumented server was crashing at a rate of about once per day with an access violation. And so an access violation is not something that you're supposed to get from the managed code, so I immediately suspected the native part of our component. And so the first thing I did is checking the source code for any change that could explain this. And I found nothing in that time frame, nothing impactful. So the next step was to configure the server to capture a memory dump the next time it crashed. You can do that by setting a registry key. Everything is properly documented on MSDN, so I won't spend time on it. It's good to note that I didn't even try to reproduce the issue locally. And the reason is that since it was happening only once per day, I figured out that my chances of reproducing it locally were really very slim. So I didn't even try. And so the day after, I had a memory dump waiting for me. And so I opened it in WinDBG. So I have it right there. And so when I open it, the first thing we see is that it's indeed an access violation with some kind of error code. We see that it happens in the CLR, in object native is locale. So at this point, I don't know what it's doing. And we see that it's trying to read the memory at the address 2B. And so as you may already know, the lower addresses in the process are marked as invalid on purpose to catch common programming errors such as null pointers. And so just as a sanity check, I try to understand where this 2B comes from. So we are reading the value from the RCX register with the 2C offset. And if I read the value of RCX, it's all Fs, which is a hexadecimal representation of -1. So -1 plus 2C equals 2B. And so from this point on, the goal of the investigation will be to understand how the value -1 ended up in that register at that point in time. So the first thing I wanted to know was exactly what code was running on the server at the moment of the crash. So I loaded the SOS extension, and then I run CLR stack, which is going to dump the managed call stack. And here we have an issue because we have some technical frames, but we have no method in there. So we were supposed to see the name of the managed method that are running, but we don't see anything. So it could mean some kind of corruption on the stack, maybe, or maybe the application crashed at a state that is not supported by the SOS extension. I don't know. But in any case, we will have to do something else. So when that happens, you can try using K, which is going to dump the native core stack instead of the managed core stack. And so at the very top, we see the object native is locale. But here we see a bunch of functions that are not resolved. So all of them are the managed functions. And the issue is that when you compile a .NET application, the final address of the function is not known yet because it will be decided at runtime by the JIT compiler. And so it cannot be written inside of the PDB symbols. And WinDBG is a native debugger, and so it's not capable of resolving the function if it's not in the symbols. So to do that, you need a debugger with a special knowledge of the .NET runtime, and that's what the SOS extension is bringing to WinDBG. And so I can take the address of this function and use the IP2MD command that is provided by SOS, which stands for instruction pointer to method descriptor, and is going to resolve the address for me. And so it's telling me that this address is the outpush cache filter.dispose function inside of Orchard. So then I decided to look at this function to understand what it's doing. Fortunately, Orchard is open source, so I was able to find it online. And so I have a stripped down version here. It's a fairly straightforward implementation of the dispose pattern. But the interesting parts are right there. We are calling monitor.isEntered, and the name reminds me a lot of object native is locale, so maybe the two are linked. And also, underscore cache key is an intern string. Locking is on an intern string, is a bad practice, but it's not necessarily wrong. Still, it's a good thing to note. So then I decided to check the source code of monitor.isEntered. So whenever you want to check the source code of the .NET BCL, you can go on source.net or use the decompiler. And so there it is. It's not actually doing much. It's just checking if the parameter is null, and then it's calling isEnter native. And then isEnter native is bound to a native function in the CLR. So unfortunately, we can't dig any further without the source code of the CLR. And the problem is that Microsoft never published the source code of the .NET Framework CLR. They published the .NET Core source code, but never .NET Framework. Fortunately, there is a trick. And the trick is to know that the core CLR repository on GitHub was created around the same time frame as .NET 4.6. And back then, the source code of .NET Core was pretty much mirroring the source code of .NET Framework. So if you go to GitHub and check out the very first commit from this repository, you will have a pretty good approximation of the source code of .NET Framework, and it may be enough for your investigations. And so I looked into it, and I searched for isEnter native, and I found this macro that is binding isEnter native to object native islockhel. So now we have the confirmation that monitor.isEntered is actually calling object native islockhel. So then I tried to check what this function is actually doing. And so here it gets a bit scary, especially if you are not used to read the source code of the CLR, because there are a lot of macros, plus it's C++, and C++ is always scary. But basically it's taking one parameter, which is the object that we use for locking, and then it's calling getThread owning monitor lock. The name is self-explanatory. It's fetching the thread that is currently owning the lock. And then it's comparing the ID of that thread with the ID of the current thread, and it's returning true or false, depending on the result. So that's pretty much what you would expect from monitor.isEntered, so no surprise there. So then I started to think about what could go wrong in there. Why would that crash? And the most plausible theory I found is that there is something wrong with the object that we are giving as a parameter for the method. So I went back to the memory dump and checked if I could get this parameter somehow. And so normally, when I need to get the parameter of a function, I will use a CLR stack with the -p parameter, stack -p, which is going to dump the managed core stack with all the parameters of the method. But as we've seen earlier, CLR stack is not working. So instead, I tried DSO for dump stack objects, which is going to browse the managed stack and dump everything that looks like a pointer to the managed heap. And I was hoping to find a trace of my parameter in there. But unfortunately, I couldn't find it. There is a string there, but that's not the right one. So it was looking bad. So then I decided to, think a bit outside of the box. So basically, when you are calling a method, the arguments are going to be stored in registers. And so if that register hasn't been touched by the time the application crashes, I should be able to find the value of my argument in there. So to verify that, I needed to know what register is being used. And so I needed to know what calling convention the CLR is using. So on Windows XE4, the CLR is using this calling convention. The first argument is stored in the RCX register, the second one on the RDX, then R8, and then R9. And so if between the beginning of the method and the moment of the crash, the value of the RCX register hasn't changed, I will be able to find my argument in there. So I decided to check the disassembly of the method. Going to zoom a bit. And so basically, I needed to find if between the beginning of the method and between the lines that crash, the one in yellow, the value of RCX has changed. And unfortunately, just right there, we are overwriting RCX with the value from the memory. So the original value is lost. Just in case, I looked around for any call to the push instruction that would store the value of the register on the stack. But I couldn't find any, so unfortunately the value is lost. So I felt like I reached a dead end, so I took one step back and I decided to think about everything I found at this point. So we know that islockhel is causing the crash. We know that isLockHealth takes only one parameter, which is the object that we use for locking. And then I tried thinking about what could go wrong. And I thought of two theories. The first one is that something is wrong with the parameter of the method, which is what I've tried to verify but couldn't. And the other theory is that getThread owning monitor lock is failing somehow, because that's the only part in the function where we are actually doing something significant. But this is a very coarse theory, and so before moving forward, I needed to refine it somehow. And so I decided to take a short pause in my investigation and check books and articles online about how monitors work in .NET, because I needed to understand exactly how everything works so that I could come up with a better theory. And so here is a summary of what I found. So let's take this simple object with a single property. And when you're going to allocate it, the layout in memory will look like this. You have the header, then a pointer to the method table, and then the actual value of the field. A little bit of trivia. When you have a reference to the object, the reference points to the method table pointer, and not to the header or the value like you could think. Let's focus on the header. The header is 32 bits wide, always, even in a 64-bit process. And it has two parts. The first part is 26 bits, and it's some kind of all-purpose storage that can contain either a hash code or the information about the thread holding the lock, in the case of a thin lock, or the index of a string block. I will come back to that. The second part of the header is 6 bits, and it's some bit flags that indicate additional information about your object. For instance, there is a flag that indicates whether the finalizer has run, some private information used by the GC, and also two bits that indicate what is stored in the first part of the header. So why do we store information on the header? Let's look at practical examples. So I have this code, I initialize an object, so it's going to allocate the header in memory, and then I call getHashCode on it. So assuming you didn't override the implementation of getHashCode, it's expected to return a value that is unique to your object, and that doesn't change over time. At first, I thought that the runtime would be using the memory address of the object, because it seems like a clever way of uniquely identifying an object. But there are two problems with that. The first one is that the address of an object can change over time, because during garbage collection, it's going to move objects around. And the other problem is that the garbage collector is trying very hard to keep all the objects compacted together. And we expect the hash to use the whole space available. So the address is not actually a good way of generating a hash. So instead, the runtime is generating a random number. But it needs to return the same number the next time you call getHashCode, so it needs to store it somewhere, and that somewhere is the object header. Note that since we only have 26 bits of storage in the header, it means that the hash code of an object actually have only 26 bits of entropy, and not 32 bits like you could think. Okay, so that's one use case. Another one is what we call a thin lock. So just like before, I create an object, and I call lock on it, because on .NET you can lock on any reference type. The way it works is that the runtime is going to use an atomic interlocked operation to store thread information inside of the header of the object, and then it will execute the critical section, and when it leaves, it's going to clear that information. When you think about it, that's one of the fastest possible ways of implementing a lock, because the header is next to your object, so you are almost guaranteed that it will be available in the cache of your CPU, so it's going to be very fast. But it's not always that easy, and so, for instance, let's consider what is going to happen if you have two threads competing for the same lock. So thread 1 arrives first, it acquires the lock, so the runtime is going to store the information in the header that thread 1 is owning the lock, and it executes the critical section. And then thread 2 arrives and tries to do the same thing. It can't acquire the lock because thread 1 already owns it. And so now, what is going to happen? Thread 2 needs to go to sleep, and it needs to be woken up when the lock is freed. So we need to store somewhere the information that thread 2 is waiting to acquire the lock. So we need a wait list, basically. And where are we going to store that since the header is already full? Another problematic case is when we combine both scenarios. So we create an object, we call getHashCode, the runtime generates a random number and stores it in the header, and then we try to lock the instance. So the runtime tries to store the thread information in the header, but we can't because it's already full. So where are we going to store that? In all those scenarios, whenever we need to store information in the header but it's already full, the runtime is going to use what we call the sync table. So it's a table allocated somewhere in memory, and the runtime is going to look for the next free entry in the table, and it's going to replace whatever information is in the header with the index of that entry. And then every entry is actually 2 pointers. We have one back pointer to the object, and then one pointer to another chunk of memory that we call a sync block. And the sync block is big enough to store everything we need, so the information about the lock, the hash code, and maybe even other stuff, I don't know. So basically, in short, the runtime is going to store information on the object header as much as possible because it's fast, but when it can't, it will instead use the sync table. And so I went back to my problem, and now I had enough information to refine my theories. And so now I had 3 theories about what is going wrong. So still the address of the parameter could be wrong, or the sync table could be corrupted somehow, or the index of the sync table that we store inside of the object header could be corrupted somehow. So in both cases, we have some kind of problem with the sync table, but in one case, it's the table itself, and in the other case, it's the index that we store in the object. So can we try to verify the theories? So I went back to my memory dump, and since we are interested in the sync table, I tried using the syncblk command, which is going to browse the sync table and dump any sync block that is currently used by a lock. And when I execute it, we see something interesting. It finds one sync block, and when it tries to read the thread info, it fails with some kind of error. So it's really interesting because we are suspecting that something is wrong with the sync table, and when we try to read it, we have an error. So then I try to use syncblk-all, which is going to read the sync table, but this time dump all the sync blocks and not only the ones that are used by a lock. And we see that it stops at index 226, which is the sync block with the error. So at this point, I'm not capable of concluding whether it means that the error happens on the last sync block of the table, or maybe syncblk stops at the first error, or maybe the sync table is so corrupted that it cannot be read past this point. But in any case, it seems that I have some kind of memory corruption. And I decided to stop my investigation there and wait for another memory dump. So why is that? It's because I have some signs that could point towards a memory corruption. And this kind of corruption could be completely random. For instance, imagine that you are writing to a wrong pointer. You will be overwriting a random part of the memory. And this time it happened to be the sync table, but maybe in the next crash it will be something completely different. So I didn't want to spend too much time on the sync table before knowing for sure that this was the source of the problem. Fortunately, by the time I reached this point in the investigation, I already had another memory dump waiting for me. And so I have it right there. And so just like before, we see an access violation. We see it happens in object native is-log-held, and we see that we are reading the memory at address 2b. So it looks really similar to the previous one. So I try loading SOS, and then run CLR stack to know what is running. Just like before, CLR stack is not working. So I try using K, and then take the top frame and resolve it with IP2MD. Just like before, it's happening in orchard in output crash filter.dispose. So it looks really good because it seems that every crash has the same symptoms, which is going to make the investigation much easier. And so then I try running syncblk, And this time we don't have an error, which is nice. And we still see something significant, that the second block has no thread info. So it means that the lock is orphaned. So basically, at some point, one thread acquired the lock, and it died without freeing it, which is a sign of a programming error. So I checked the source code of Orchard to understand how we could end up with orphaned locks. And so what I found is, so basically Orchard is an ASP.NET MVC application, and it's using two events as part of its locking mechanism. In controller.onActionExecuting is going to acquire the lock, and then in another event, actionFilter.onResultExecuted is going to call outPushCacheFilter.dispose, which is going to release the lock. And the thing is, for this to work, you need both events to be raised on the same thread, because only the thread that has acquired a lock can free it. But ASP.NET makes absolutely no guarantee about that, and it's entirely possible that the two events are raised on separate threads, which is how you end up with orphan locks. So this is not great. That's not something you want to happen in your application, but it still doesn't explain why we have an access violation. And since this could have been caused by our instrumentation, I absolutely needed to get to the bottom of it. And so I was a bit out of leads, and so I figured out that it was time to focus on the disassembly. So yeah, we have a bug in this version of WinDBG where the disassembly window is empty until you run one command. And so basically, I needed to understand what were we doing exactly in the function at the moment of the crash. And I don't know about you, but personally, when I see that, I don't understand much. I know what most of those instructions are doing individually, and I'm saying most, not all of them, but I'm completely unable to reconstruct mentally the flow of the program like I would do with some C# code. But fortunately, we already have the C++ code as a function, and so it's just going to be a matter of mapping the C++ to the native instructions. And the way I do that is by looking for instructions that are easy to recognize. So for instance, this one. Here we are reading the memory at some address, and thanks to the symbols, it was resolved to G_pissing table in the CLR. And so then, if I check the source code and I find one place where we read this table, I know that this line of code was compiled to this instruction. So I check the source code, and we are not using G_pissing table anywhere. So that usually means that one of the functions that you are calling got inline during compilation. So you also need to check the function that you are calling. So I checked getThreadOwningMonitorLock. And so this one is much bigger, so I'm not going to try and understand what it's doing for now. All I'm interested in is it using G_pissing table somewhere? And it turns out it is. And also, I got lucky because it only used it at one place. And so I have the guarantee that this line of code is mapped to the native instruction that we saw. So then I kept looking for stuff that you can recognize. And here we have two if blocks, and each of them is checking if some bit flags are set. And if we go back to the native instructions, we have two calls to the BT instruction, and BT stands for bit test, which check if some bits are set. So there is a good probability that those two BT instructions are coding for those two if blocks. So to verify that, I check the value of the constants that we are testing. And so, for instance, bit sync block is hashcode, has this value, which is this binary representation, which means check if the 27th bit is set. And 1A in hexadecimal is 26, which means that this instruction is checking this constant. So here you may be confused because we are talking about the 27th bit, and we are calling BT with the value 26. And the trick is that BT is 0 based. So BT0 is testing the first bit, BT1 is testing the second bit, and BT26 is testing the 27th bit. So then I did the same thing for the other constant, just to be sure. So bit sync block is hash or sync block index. This is a binary representation, and it means check if the 28th bit is set. And so 1B hexadecimal is 27, and so this is this native instruction. And so every time I was able to map a line of C++ to the native instruction, I annotated my code so that I would little by little reconstruct my mental image of the function. And so I kept looking for interesting stuff. And here we have test RCX RCX. Whenever you are testing a register against itself, you can be almost sure that it's either a null check or a false Boolean check. So I check the source code. And here we have a null check. So there is a chance that it was compiled into this instruction. So assuming this is the case, it will mean that the RCX register is storing the address of pthread. So let's see where it's coming from. It's coming from the memory at address RDX plus 8. RDX comes from RAX plus RCX times 8. And RAX contains the address of the sync table. So given that RAX contains the address of the sync table, RAX plus RCX times 8 sounds a lot like if we are reading the sync table at a given index with the index stored in the RCX register, which would mean that this instruction codes for this line of code. Assuming this is the case, it will mean that the result, which is a pointer to the sync block, will be stored in the RDX register. And so then when we read RDX plus 8, it will mean that we are doing calling getMonitor on the sync block and fetching the m_holding thread field. So here it's a bit of a stretch, and so I really needed to verify this before moving forward. And so basically what I needed to verify is reading the memory at address RDX plus 8 when RDX stores the address of the sync block the same thing as calling getMonitor on the sync block and fetching the m_holding thread field. In other words, I assumed that I had the sync block in the RDX register, and so I tried to figure out what was at RDX plus 8. So to do that, I checked first the source code of the getMonitor function. All it's doing is returning the address of the m_monitor field. And then I checked the sync block class, and m_monitor is the first field of the class. In memory, the fields are going to be stored in the same order as they are declared in the code, except some exceptions. So that will mean that m_monitor is going to be stored at the beginning of the object, and so is going to be stored at offset 0. So at offset 0, we have the aware lock that is stored in the m_monitor field. So then I check the structure of the aware lock, and it has 3 fields. The first one is m_monitor held. So it's the first field, so it's going to be stored at the beginning of the object at offset 0. And it's a long, it's 4 bytes, so it's going to end at 0x4. Then we have m_recursion is going to be stored next to the previous field, so at offset 0x4. And it's an unsigned long, it's going to be 4 bytes, so it's going to end at offset 0x8. And then we have m_holding thread, which is the field we are looking for, which is going to be stored next to the previous one, and so it's going to be stored at offset 0x8. And so we have the confirmation that this native instruction is the same thing as calling getMonitor on the sync block and fetching the m_holding thread field. So I annotated the native instructions with my findings, and at this point I felt like I had enough information to focus on the crash itself. So here we are calling test RCX RCX, which is if pthread is null. And so the way it's going to work is that it's going to set the 0 flag of the CPU if the value of RCX is 0. So basically it's going to set the 0 flag if pthread is null. Then we have this GE instruction. GE is going to jump to the target address if the 0 flag of the CPU is set. So it's going to jump if RCX was 0. So it's going to jump if pthread was null. Then we have the line that caused the crash. And if we got there, it means that we didn't jump at the previous instruction. So it means that RCX wasn't 0, and so pthread wasn't null. And so we were there. That will mean that we crashed when calling getThreadID on pthread. And so getThreadID tries to fetch the ID of the thread. And so to move forward, we have to verify if the thread ID is stored at offset 2c, because we are crashing when reading the offset 2c from pthread. So I'm going to do the same verification as before, but without the fancy drawings. we're just going to count how much memory is used by all the fields before the thread ID and see if it sums up to 2C. So m_state is a thread state, is 4 bytes. We have an unsigned long, it's 4 bytes. We have 3 pointers. It's a 64-bit process, so it's 8 bytes each. Then we have a dword. Dword is always 4 bytes. And then finally, we have our field. If we do the sum, that means there is 36 bytes before the field. And 2C is 44 in decimal, so it doesn't add up. So does it mean that my theory was wrong? Well, not quite, because if you pay close attention, you will see that thread inherits from I and none. And if you check the source code, you will see that I and none has some abstract functions, which means that thread will have some virtual functions. And in C++, when an object has virtual function, it's going to expose a vtable. And the compiler is going to generate kind of like an additional field at the beginning of the object that is going to store a pointer to the vtable. And since it's a 64-bit process, that pointer is going to be 8 bytes. So if we redo the math, we have 44. And so we have the confirmation that the thread ID is at offset 2C. And so we have the confirmation that we crash when reading the thread ID. So that will mean that the crash occurred at this function, which will mean that pthread will be -1. Because if you remember what I checked at the very beginning, we are reading memory at arrest 2B, which is 2C plus -1. So now the question is, where does pthread comes from and why is it -1? So this time we need to focus on getThread owning monitor lock and actually understand what it's doing. So we start by calling getBits. GetBits is going to read the header of the object that we use as a parameter for the locking. Then it's going to check if the isHash or SyncBlock index bit is set. So if you remember my explanation, the header has 2 parts, one all-purpose storage, and then a few bit flags that indicate, among other things, what is stored in the first part. And so here we check if the first part is storing a hash or the index of a SyncBlock. We know that is the case because if that wasn't, then we would have executed the else part of the if, and so we wouldn't have gotten to the crashing instruction. And so then we check the flag that indicates whether it's a hash code. We know that's not the case, otherwise we wouldn't have gotten to the crashing instruction. And so at this point, we know that the header is storing the index of a SyncBlock. So if you remember my explanation, it means that the runtime tries to store something in the header, but it was full, and so it moved everything to a SyncBlock, and instead stores the index in the header. So then we apply a bit mask to retrieve that index, and then we read the sync table, and we fetch, we read the sync table at that index, and we fetch the pointer to the SyncBlock. So if you remember my description of the sync table, we have the index, so we get the entry at that index, and then in that entry we have a pointer to the SyncBlock, and we are fetching that pointer. And then now that we have the pointer to the SyncBlock, we get the part of the SyncBlock that contain the lock information, and more specifically, we get the address of the thread owning the lock. And then pthread is not null because it's -1. And so we get to the crashing line. And so that will mean that we are crashing because we have the value -1 stored in the m_holding thread field. Which begs the question, why would we end up with the value -1? But first, before moving too far, let's try to verify it. So to verify it, we will need the address of the SyncBlock. And if we go back to our annotated native code, we found out that at this point, we have the address of the SyncBlock in the RDX register. And the RDX register is not touched past this point. We never change the value, so it should still be intact in the memory dump. So if I get back to my memory dump, I'm not going to need that anymore. And I read the value of the RDX register, I should have the address of the SyncBlock. And in fact, if I copy this value and look for it inside of my WinDBG window, I find the output of my syncblk command in the second column, which contains the address of the SyncBlock. So we have the confirmation that this is indeed a SyncBlock. And interestingly, it's the orphan SyncBlock. So then I can use, I need to copy it, sorry. There we go. Then I can use a dd command for dump d words to read the memory at this address, and it's going to display it by chunks of 4 bytes. And then I can try to map those values to the values of the sync block. So basically, I know that the structure of this part of the sync block looks like that. I have those values in memory, and I'm just going to map them. So m underscore monitor held is the first 4 bytes, so it's going to be 1. M underscore recursion is the next 4 bytes, so it's going to be 1. And if you go back to the output of syncBLK, you see that you have monitor held and recursion columns, and both of them are 1. So it seems like we are on the right track. And then m underscore holding thread is the next 8 bytes, so it's all f, and so it's -1. So we have the definite confirmation that the sync block is storing the value -1, which is causing the crash. So we still need to figure out how this value ended up in the sync block. So fortunately, -1 is a very significant value, easy to recognize. And so I was able to scan the source code of the CLR until finding all the places where we are storing -1 in the sync block. And there is only one. So it's happening in the obj header getSyncBlock function, which is called during the promotion for a synlock to a sync block. So basically, this is called whenever the runtime tries to store something in the header is full, and so it tries to move that to a sync block. This happens in getSyncBlock. And so we have the part where we store -1 in pthread. And above, we have a very interesting command saying that the lock is orphan, which is consistent with what we found so far. Then if we check where it's coming from, we get there if pthread is null, and pthread comes from this psynlog thread ID dispenser, ID to thread with validation. So that's a mouthful. And so let's check what it's doing. So more C++, yay. I'm not going to explain this one, but what you need to know is basically the function is taking an ID, and it's returning a pointer to a thread, and internally, it's using some kind of table to get that pointer. So why would the runtime need something like that? Well, let's go back to my explanation about thinlocks. I told you that the runtime is going to store some information about the thread inside of the object header, but I never explained what kind of information it's going to store. Well, ideally, the runtime will need the address of the thread, because it needs the address to fetch the thread instance. Unfortunately, the address of the thread is going to be 32 or 64 bits, depending on the bitness of your process. And we only have 26 bits of usable space in the header, so it's just not going to fit. Instead, the runtime is going to store the ID of the thread. So here you may be thinking, how is that helping? Because we are still trying to store 32 bits instead of 26. And the trick is that the runtime will try to aggressively reuse the thread IDs to keep the maximum under 26 bits. So what I mean is, as soon as the thread is going to die, the next thread that spawns is going to reuse the same ID. And so to get above that limit, you need to spawn more than 67 million threads. And given that every thread has 1 megabyte of stack, you're probably going to run out of memory way before getting even near this limit. But the runtime still needs the address of the thread, not the ID. And so it's also keeping a table that allows it to associate this ID to the address of the thread. And this table is a synlog thread ID dispenser that we've just seen. All right, so what do we know? We know that the access violation is caused by the value -1 stored as a thread address in the sync block. We know that this happens when a synlock is promoted to a sync block, but the thread ID is missing from the table. So in this case, the runtime is going to store -1 instead of the address. Which begs the question, in what condition can the thread ID be missing from the table? We also know that thread IDs are aggressively reused to keep the maximum ID under 26 bits. And the way it works is that when a thread is dead and the finalizer is going to run, it's going to clear the thread ID from the table so that it can be reused by the next thread. And that's how it can be missing from the table. And so that will mean that the crash will happen. Well, the value will be missing from the table if the thread died by the point where we try to fetch its ID. So I feel like at this point I had complete enough understanding of the problem to try and write a repro. So I switched to Visual Studio and I wrote this code. So basically what I'm doing is I'm creating a bunch of objects, nothing special about them, it's just new objects. And then for each of those objects, I'm creating a new thread. A new thread will try to acquire the lock. So at this point, the object header is empty, so the runtime is going to store the ID in the object header, and also is going to feed the table that associates the ID to the address of the thread. Then I let all those threads die, and so I will end up with orphan locks. And then I force a garbage collection to be sure that the finalizer of the thread is going to run. And when it's going to run, it's going to clear those IDs from the table. Then I enumerate again on my objects, and this time I call getHashCode. So runtime is going to generate a random number. It's going to try to store that number in the header, but the header is full. So it's going to get a sync block in the sync table, store the index of the sync block in the object header, and moves information inside of the sync block. And when doing so, it's going to resolve the ID of the thread and try to get the thread address so that it can store it in the sync block. But when doing so, it won't be able to find it because it got cleared here. And so instead, it's going to store -1. And so here we have all the conditions for the crash. So I just enumerate on my object, and I call monitor.isEntered, which is going to call isLockHeld, which will cause the crashing instruction, because we check if pthread is null, but we don't check if pthread is equal to -1. So if I run this, you will see that it crashes with a fatal execution engine error. So I don't see the access violation in there because I'm running with the debugger and it's changing the error handling a bit, but it's exactly the same crash, and as a matter of fact, I have the same error code. So we've identified the problem, but there are still a few unresolved questions. And the first one is, why is the baseline server not crashing? Because if you remember my test environment, I have 2 servers running Orchard, and only the instrumented server is crashing, even though we just figured out that it's a bug in the .NET runtime. And the trick is that Orchard uses a finite set of lock as part of its cache mechanism. So what I mean is the lock are used for caching the output when you try to load a page. And since we use automated traffic, we always load the same page. And so it's always the same lock that is going to be used. And the crash only happens if an orphaned thin lock is promoted after the parent thread was collected. This is a very precise set of conditions, and it's especially unlikely to happen in an ASP.NET application because it's going to use a thread pool, so the thread is unlikely to die. And the thing is, if all the locks got promoted without those conditions being filled, then the crash cannot occur anymore. So basically, when you start the application, it's going to use thin locks. Then they are going to get promoted. So here you have a window of opportunity for the crash. And then if it didn't crash, you can let your application run for days, and it's not going to crash anymore. And the thing is, the instrumented server is redeployed every time we do a change in our code base, which is multiple times per day, whereas the baseline server is never restarted because we never need to restart it. And that's the only reason why the crash was only occurring on the instrumented server. There's another question. What has started the incident? This is a bug that has been in the .NET runtime for as long as I could find. And in fact, it's still in the .NET runtime today. So why did it start crashing someday? Well, this time it's our fault. I'm saying that we run Orchard, but we are not exactly running it. Basically, we modify it to add some workload just to better test our instrumentation. And since this is asynchronous workload, we changed to use an asynchronous controller, because by default, Orchard uses a synchronous controller. And if you remember, we end up with orphan lock, which is one of the conditions for the crash, if those two events are raised on separate threads. And it's an implementation detail, but when you use a synchronous MVC controller, those two events are always going to be raised on the same thread, simply because since there is no asynchronous operation, then ASP.NET has no reason to switch the thread. And that's the reason why this bug has never been found inside of Orchard. And it's us, by switching to an asynchronous controller, that created the condition for the crash. All right, so to wrap it up, the more complex investigation, the more important it is to verify every theory or assumption. So if you've seen the way I proceeded, I try to break down the big problem into smaller problem, and then every time I spend all the necessary time to verify the assumption I was making. And by doing so, you make sure that you are little by little making progress. Because if you try to resonate about the whole thing by basing yourself on fake assumption, false assumption, sorry, then you're going to get lost eventually, because your reasoning is not going to work, and you will not be able to understand where you did something wrong. So it's very important to verify everything at every step on the way. Also, take the time to refresh your knowledge on the affected area. That will allow you to make better theories about what is happening. So in this case, when I started suspecting that it has something to do with monitors, I took a break, I checked books, I checked articles online until I had a clear grasp of how monitors work in .NET, and it really helped me to make better theories about what is happening. And the last piece of advice is don't give up. Raymond Chen, which is the author of the All New Thing blog, says that debugging is an exercise in optimism. And I agree 100% with that. You're going to be wrong a lot of times. And it's part of the process, so it's OK. And every time you are wrong, you are going to learn something new about your problem. And if you don't give up, eventually you should be able to get to the bottom of it. If you like it, there are more investigations on my blog, so make sure to check it. And feel free to ping me on Twitter if you want. So that's it. And I think we still have plenty of time if you have questions about it. Well, no question about after showing that much assembly code. I don't know if that's a good sign. Yes? Sorry, can you speak louder because I can't hear you. Well, this is release code. So you use exactly the same kind of tool. Of course, a release code is going to be harder to read, but most of the times your crash dump is about to be release code. Because, well, usually when you use a crash dump, it means that the crash is occurring in production. Otherwise, you would just directly attach a debugger. And so, yeah, most of the time it's going to be release code. And it's fine. If you have symbols, it's going to help you a lot. If you don't have symbols, good luck, but the information is still there somewhere. I think there was another question. Yes? Or it's going to be tricky. I'm not hearing anything.
How long time did you spend on this?
Oh, so the question is how long I spent on this? I think about 3 days. Yeah, that was a 3 days investigation.
When do you think this is going to be fixed?
I don't know. Probably when I stop getting lazy and fix it. I already opened the PR on GitHub where I explain everything about the problem. Just need somebody to pick it up. We have two problems with this. The first problem is that it's very hard to understand why the runtime is doing that. I think it's at least as hard as .NET 4, and it's probably even harder than that. It's hard to know why at some point somebody decided to store -1 rather than null for the thread. And we see the comment, the lock has been orphaned, so it was a conscious decision. And the other thing is that this bug is incredibly unlikely to happen because, well, imagine that it's going to happen to you. You're going to think about what is wrong in my application. You will see that you have orphan locks, so you're going to fix that because nobody leaves orphan locks in their application. And then the problem is gone, so you're not going to think about it anymore. So yeah, it's very likely to stay there for a while. So, yeah?
In your example, you created, when you reproduced it, you created something like 16 threads. Was there a specific reason for creating one?
Okay. So the reason so the question is why in my repro I created 16 objects instead of just one. And that's because, well, I did not explain the details about going back, about the ID to thread with validation. But basically, I took some shortcuts in my explanation, and the crash is only going to happen if we meet that. So basically, it's going to use a table. That table has some, I don't remember what it's called, but basically it's a linked list, and it's going to store a list of, it's going to store a free list to know how to reuse the node. And there is an implementation detail that makes that you're going to have this problem only if you meet this if ID. So there is this if ID inferior or equal of is ID, and you're going to have null only if it's bigger. And basically, because there is some precise condition inside of it, by creating 16 objects, I make sure that it's going to happen. Because if I have only one object, it's actually going to reuse an old. So that's actually interesting because there is another bug in there that I didn't try to explore. But basically, if the ID is lower, it's going to fetch an old node of the linked list instead of returning null, which means that it's going to return the address of a different thread. And so it means that for your orphan lock, it may actually get the address of a different thread, and I'm not sure what the consequence will be. But in that case, it won't crash. So I think that's it. So thank you, everybody. And in any case, I will be around if you want to discuss.